Good afternoon, everyone. The House of Sultan Chand Sons Private Limited and Method AI extend a very warm welcome to all the participants to today's data science webinar. It feels nice to have you all here, and we thank you for that. A bit about the House of Sultan Chand Sons Private Limited first. We are pioneers in the field of book publishing in post-independence India, catering to students from pre-primary to university level, churning out over 600 regular titles, besides adding new ones to our stable year after year. Known for competently written, elegantly produced, and reasonably priced books, our publications are widely prescribed in reputed schools and colleges across the nation as well as in some other countries. Our authors are distinguished academicians, professors, and educationists with vast experience and expertise. We are proud to be associated with them. I now introduce you to the host of today's webinar, Dr. Sachin Gupta. Besides being the author of 2 data science books for classes 9th and 10th, he is also Dean, Academics and Research and Professor in the Department of Computer Science Engineering at MVNU for the past 7 years. He has also been HOD Computer Science Engineering and MCA Department in Dronacharya Group of Institutions, Deputy Director and Head of the Computer Science Department in Chandraprabhu Jain College of Higher Studies affiliated to GGSIPU, Delhi. With a teaching experience of over 20 years, which includes teaching undergraduate and postgraduate students and researchers, Dr. Gupta's academic pursuits have been fairly meritorious, winning him several awards, distinctions, scholarships, including the Certificate of Academic Excellence by GGSIPU. Dr. Gupta has contributed to various journals, conferences, and books for schools and higher education, both nationally and internationally. His achievements are truly commendable. May I now request the man himself to take you through today's webinar, Dr. Sachin Gupta. Have a great day ahead. Thank you.
A very warm welcome and good afternoon, everyone. All those who have joined the session today. We are into the third week of sessions on knowledge series in data science. And we are picking up topics which are particularly useful for the faculty members and students who are learning either statistics or planning to take up data science. I hope I am audible and my screen is visible to everyone.
Yes, sir, you're audible.
Okay. So the topic for today, we are going to take up with population and sampling. I was actually dreading taking this topic up because central limit theorem is theorem in statistics, which is at the heart of statistics. It actually begins the borderline of probability also, where how do you predict something, and it is so abundant in nature, and yet it is very less intuitive. I mean, by intuition we'd not be ever able to explain how central limit theorem works or why is it actually even working. So I'll start with some basics and then we'll go on into the session in detail. So a very happy new year to everyone in the audience. I have been introduced by Malik sir amply, and I just want to add that I've been struggling with information technology since 20 years, but I'm fortunately yet to give up, so that is a win. We are going to discuss basics of problem solving as we discussed in the last session. I'll just continue from where we left off with the statistical problem solving method, some demo on CodeApp. And we will talk about the problem solving process in general. What is the purpose of variability? How variability helps in data analytics? What is population? We have to talk with the law of large numbers also, law of large numbers. And eventually we'll talk about the central limit theorem. Some terms of these we already know, some of them we are going to learn in the session today. So the very first thing that we are going to start with is an investigative question, that any statistical process starts with an investigative question, that we want to investigate some process, some phenomena, something which is happening. Why is it happening? What are the ways in which it is happening, and so forth. And every statistical process goes through 4-step iteration, where we initially create a investigative question. We collect or consider the data if it is available. We analyze the data and we interpret the result. At every phase, there is a possible feedback back to either formulating the question again, or while analyzing the data, we might need to change the question, or we might need to consider or collect more data. Or while interpreting the results, we might again go back to either of the previous stage, including collection of data or formulation of statistical question again. So this is the whole statistical problem solving process that works. The key element here is the data that we are going to collect about the statistical process. And there comes the question of variability. Variability is the foundation of statistical investigation. I mean, if anything is constant, it is not going to give you anything more than a constant value whenever you are going to investigate it. So look at the picture here. If we see that there is a lot of variability in the image, if you want to check out, just find out what all is variable. You would be looking at 2 genders all across the image. But in addition, the heights of the people are variable. That means height can be a statistical variable that we can actually consider using in a statistical question. Similarly, hair color of people would be different. The weights of people might be different based on their body shapes. They may be of different ages. So we have people here right from infants to old age people. The eye color of people may be several different. The skin colors, there are a lot of variations when it comes to people. So these are some of the possible variations which we are actually using here. And then with this, we are actually again going to look into another statistical question that we are going to investigate today, that actually talks about the height of each student in your group. So we just look at one simple variable here that speaks about, let us say the question is the height variable? Obviously, you are going to be able to see that if there are a lot of students in your class group, the height absolutely is variable. Some people are tall, some people are short. There is a lot of difference that actually comes to varying heights. Then let us take the question a bit further. If we have to investigate the height of each student in your classroom, that means the first thing we were trying to find out the heights of people in my friend circle. So there may be a couple of people. There are just, let us say, 8 or 10 people in my group whom I can straight away ask, what is your height? I can record them. I may actually investigate the process. Pursuant to this, I might want to actually find out the height of each student in my class. Then how do I collect the data? That becomes a bit tricky because I would need to now ask each one of these students either to fill a form, or I have to take help from my teacher who will be able to actually get me the data value by recording the height of each of the students. Or it may eventually be even be that I approach each of the students individually to ask them about their heights. All right. Let us take it yet another step ahead. If I may now want to find the height of each of the students in my school, I'm not just restricting myself to my friend circle. I'm not just restricting myself to only the people in my class. Let us say there are classes from class 1 to class 12, and there are a lot of sections, and I want to now find the height of each student in the school. Now, collection of data becomes tough because my teacher alone would not be able to help me. I cannot go to each of the students one by one. and ask them to share their height data. So this becomes a very tough process for me to able to actually find out the heights of each of the people across all the classes. It's a hard job. The data collection is a hard job. And if it were to go any further beyond this, let us suppose we want to find the height of each school student in our city, or maybe even all over India, or the entire world for that matter. How about collecting the data now? It is almost close to impossible, but yet statistical processes allow. That means by statistics, if I were to find out what is the height of 18-year-old people across the world, so there is a rough estimate that on the average, people are roughly 67.5 centimeter high, inches, sorry, 67.5 inches high. And that is something that we actually have gotten through the statistical process. But the problem is now collecting the data, which is almost an impossible task. We have to find some way of doing it. So that actually helps with sampling. That is where sampling comes into picture, that we take a representative of population. Population is that interest set, the set of people or the set of objects or the set of phenomena from which I want to actually take the data. So if I want to analyze statistically the weather of Delhi, so my population would be the weather of Delhi or the weather data of Delhi for all the days for the duration I want to collect it. If I want to collect the statistical investigation into my study group or my friend circle, then only this set is the population. That means my population set is very small. There are only a few number of items here which I want to observe. For this set, my population set grows. That means I have roughly around 50-60 people in my classroom. My population set is a bit bigger. But when I want to find the height of each one of them, then I am actually working on a population characteristic that I am trying to find the height of the entire population. For the entire school, my population set has grown from 50-60 to maybe 1,000, maybe 2,000, depending on the size of the school. And that is where population actually starts increasing. But I have a problem, that is the data collection becoming tough. And for the entire, say, city, the population may be a couple of lakhs. For the country, we are talking about a few billion. For the world, that would be hundreds of billions. And that's where we are having a real problem, that we have a data collection absolutely close to impossible. But what if there was a method which would allow us to only take representatives? That means I may take a couple of people from my city, I may take a couple of people from some other city, all across the globe, taking data from the people of a certain age over a certain city, and just take them as samples of the population or representatives of the population to find out that whatever characteristic that we were trying to find for the population, now we are going to use a sample for the statistical investigation. So sampling is one phenomena which allows you to make huge population statistical analysis possible. Now, when I'm saying population, that does not necessarily mean human population. It can be population of human, it can be population of all cats, it can be population of all dogs, it can be food items, it can be anything that I want to observe. By population, we are not restricting ourselves to human. Population is any set from which we are looking forward to derive the data from. That is population. And if I'm taking a subset of that, some strategically chosen subset I may add. So that part is sampling. And by sampling, we are trying to pick up some data which is useful for us and which is allowing us to be able to find out what is the characteristic of a population. All right. So this is what we are going to actually demonstrate today. We are going to look into some data that I am going to import on the Method AI platform. So we can say, so we have just recently introduced CODAP on the Method AI platform, where it is a data analysis tool where I'm just going to open a new document which has a lot of data for you to be able to see. So, okay. I'm just trying to import the data for 25,000 18-year-old students. So you see in my data set, when I'm trying to import the data, Codap tells me that I may actually work with 5,000 rows in the beginning. It's a huge data. There are total 25,000 entries. And I can select every, say, fifth element in a row or fourth element in a row or ninth element in a row. Anyhow, this is the way of sampling actually. So I may want to choose randomly select, let us say 8,000 rows all in all. So this is the data that I'm going to import. So essentially what I'm looking at is data of 18-year-old students, total 8,000 in numbers. Okay. And that's a beginning. So if you see the cases here, there is it's building. The index talks about which number we are having. Then which elements have been imported. They are randomly selected from my data set. So from 1, 2, 5, 8, 9 across 25,000 rows, which row have we selected? That is the index. So there is no actual pattern between 64 to 63 to 64 is available, from 64 to 68 and 69 is available. Then randomly we are choosing the rows. For each of the row, there is a height and weight available. And let us now go on look into how the data is distributed. So distribution tells you something about that how commonly are the elements occurring. That means how many students, 18-year-olds would have commonly occurring heights, how many of them would have rarely occurring heights and so forth. So let us try to plot the height data on a graph. So this is the graph of all the heights. It will take a while to settle down because there is a large amount of data on my screen. Okay, so this has settled down. And look at the beautiful shape of the curve. This is something that we call as a normal curve or the bell-shaped curve. And in statistics, all through the nature, we say that any large continuous data randomly generated from a lot of data entry, that would always appear to be normal. That means certain values would be at the, that means the maximum values would be close to the average. And as we go away from the average, the number of values are going to actually start decreasing. So we would see a majority of the people are going to be near the average height of 67.5. And as we go from the average towards the less, so 60.28 inches is the least and 75 inches is the maximum height. So we may actually again check it with the help of the mean, that the mean height here is 67.97. So 18-year-olds mean height is 67.97 inches. Right. This is about the whole population. What if I were to actually just draw a sample? Let us say we want to draw a sample of say 200 or 300 from this, and let us try to draw a plot. So for sampling, we are going to take a plugin here for the sampler. And from this, we are going to collect some data element. Let us say we are going to collect only 100 samples from this population. Well, let's make it 200. It will take a while. working with big data has a distinct disadvantage. Even with a 16 GB of RAM, my laptop would take a large amount of time to load this much amount of data. Okay, so we can start. You will see the sampler is going to actually, we are going to collect 100 items and 3 such samples, right? We may have, we are going to draw 100 items 3 times from this data set. This is going to populate my table here. Too much data. I hope it works, or I would have to take a smaller sample. Okay, barely working. All right, so I have my samples available here. Let me close this chart. Let me close the sampler also. And let us only work with the data that we have just generated. So there are only 300 cases here. I hope my job would be easier now. So this is randomly chosen sample from the population, which was supposedly initially 25,000 cases. We have only imported 8,000 out of 25,000. Out of these 8,000, we are taking samples, only 300 cases, and let us see how they plot. So on a graph again, we are going to plot the height in inches. This time it should be actually working fine. So my data is immediately plotted. We had the mean height at 67.59 earlier. Let us look what is the mean height here. So 67.9 was the mean height for all the 8,000 population cases. And by the law of large numbers, we now see that even while taking a sample, if a sample size is reasonably good, then the sample imitates the properties of the population. So when I said here that whenever we are sampling, sample is a representative of population, not only in the terms of taking up some data cases from it, but it is also a representative of the population in the terms of that it has these similar statistical properties as the population. Ideally, it would be having almost the same mean as the population. It would almost have the same variation as the population. It would almost have the same standard deviation as the population, same median as the population, and so forth. So if my sample is normally, if my population is normally derived, the sample would always have the same properties as the population is. This would also have an almost bell-shaped curve that we had earlier from the, not exactly the same as the population, but almost similar. So this is about the law of large number, that if there is a large data set from which we are deriving a sample which is fairly good. I mean, I could have done only 30 cases. So let us close this back. Let us take a plugin. Let us take a sample which is hardly 50 items, right? And collect 3 samples again. So from the collector, we are taking 50 items now instead of a lot. And let us start it. Let us take a smaller sample. Instead of 300, we are just going to take in 150. Okay, remember the mean value 67.9. Okay, it is working. Finally. So here I have just slowed down my work so that you can see that sampling is actually being done. It is picking up some random values from my data, populating them one by one into this. I can increase the speed of this sampling, so the process would immediately go faster. My sample is completed. So I now have 3 samples, each there just 150 cases. Let us draw the diagram again and see if the law of large number holds. 67.9 was the value, and if we now check the mean, this is 68.16. This is just barely a little different from that. So the mean is following that. Given a good amount of sample, we would be able to actually match the exact population. But as we increase the number of samples, the value gets closer to the actual mean. So that is basically the law of large numbers. And the hero of the discussion today was supposed to be central limit theorem, not the law of large numbers. But I just wanted to actually tell you that what happens when we sample and what is the distribution of the samples like. So the distribution of the samples is almost like exactly as per the population, and it follows the properties of the population very closely. Okay. So if I have a normal distribution, this would actually look like a normal distribution. If I would have had an exponential or some other shape of distribution, then the sample would also have followed the same. All right. So let's close this down for a bit. Let's go on into the central limit theorem now. I hope there are no queries so far. If there are any, I would like to have them on the chat screen or from the window. Okay, no queries so far. Let us take it further. So I'm now going to take a different kind of distribution, which you must have actually, it's very intuitive to understand. You might have actually tried to call some call center sometimes for any query resolution, or maybe for your mobile, any call center. So the data here is about the waiting time at a call center. And by and large, most of the calls are actually completed within a very short amount of time. But some calls have more waiting time than the others. Some still have more waiting time. So taken from a call center, this distribution shows that this is a skewed distribution. We have a total of 2000 cases. So my population size here is 2000. That means I am having data with 2000 waiting times of, or 2000 customers waiting time for a call center is my data. Pushed into a distribution mode, we can plot it like this. I have also created a dot plot with box plot here, which tells you that the first quartile deviation is 33.575. Then the median waiting time for the customers is 141, and the upper quartile is 384. But the minimum waiting time may be 0, and the maximum waiting time even can be 1458 seconds. So this is the amount of waiting time that somebody might have to wait at the max, and this is the waiting time which somebody has to wait at the minimum is 0. So let us try to follow the law of large numbers, that if we derive some samples from it, what would be the shape of the samples distribution? Mind you, take my words, I'm talking about the samples distribution. Average processing time is a normal shaped curve that you can see with a mean value of 5.03 is the normal average processing time, right? We are not interested in this chart. We are only interested in the distribution of what is the waiting time now. So I'm going to actually keep this. So let us sample it. Let us take in 100 samples or 200 samples from the call center service time. take the plugin again from the sampler. We are going to use the collector and let us sample 200 items from this distribution and collect only a single sample. For the time being, I'll make the simulation fast so that we get so this is the call center service time. From this data we are deriving and we start. So we are just picking 200, that means 10% only of the total cases. 2000 cases were there. We are picking 200 from the sample and we are going to plot the distribution of the waiting times against this distribution. So by the law of large numbers, ideally this should match the properties of my previous distribution, and let us see how it does. So if you look closely, you see the exponential, the distribution for 200 cases is also exponential. Let us draw the statistical characteristics of it. The block plot, the median, show measure labels. So the median here is 155. That means we have a different value of the median, not very far off, because there was a lot of range. There, the maximum value is 1432. It has been taken. Here we had 1415 or 1498 and so forth. But the shape of the distribution resembles the shape of the distribution earlier. I mean, my sampling is following the law of large numbers for sure. All right. This was for showing that my sample closely resembles the population. Now, central limit theorem talks differently. It actually says that I'm not going to take the samples now. I'm going to take the average of these samples. Okay, let me create my tables first, and then we are going to able to see. So I'm removing all the different tables that we created temporarily. Now what I'm going to do is I'm going to take some samples and take the average waiting time for each sample. Okay, so look closely what we are going to do. I'm going to run the collector, but I'm going to take only 30 items per sample, and I'm going to collect 100 different samples from the data set. So I'm going to randomly pick 30 items out of 2000. That would create my first sample. Then I'm going to again randomly pick 30 items from the data set. That would be my second sample, and so forth. So I'm essentially doing 100 samples, each containing 30 items randomly picked from here. All right. That is my part one. And in my part two, what I will do is, let us collect the data first, and then we are going to work it up. So this is creating samples. I'm collecting 100 samples total, all in all. You'll see this is a very, very interesting use case of the central limit theorem, that it would be a very surprising distribution for what we are going to create. Just keep in mind the law of large numbers also. Okay, so this is the new data that we are going to work with. Okay, let me show you the data first. So for the first sample only, check out, there are 30 total values in the first sample. In the second sample, there are 30 items. In the third, fourth, fifth, every subsequent sample has 30 items each, right? So for the first sample, there are 30 items. I can expand it. So you see all the 30 items of the first sample here. If I want to plot it, you may want to see that for the first sample only, what is the waiting time? Okay, this is showing for all the samples, not just first. Okay, so see, the properties of my distribution are similar to what we had earlier. All right. Now we'll do something other than this. This was the law of large numbers. We have already seen it in work. I want to now find out that the first 30 items, what is the average waiting time of these 30? So let us create another attribute here. Let me give it a bit of size. I'm creating another attribute here. Let me call it the average underscore weight. So this average underscore weight is going to collect for each sample the waiting time, that the average of the waiting time. So let me edit the formula for it. It should contain the mean of the waiting times across each sample. And this is, so check out. For the first sample, the average waiting time is 218. For the second sample, the average waiting time, sample mean for the first 30 items, the average waiting time is 218.68 seconds. For the second sample, the average waiting time is 219. For the third sample, the average waiting time is 193 and so forth. So for each of the 100 samples, I have got different average waiting times. All right. Now, what do you expect the plot of the average waiting times to be? Should it be almost like close to the distribution like here? Here comes the central limit theorem. CLT says that if I am taking independent samples and I take the mean of those samples, then the distribution of these means is always going to be normal. Normal, that means bell curve shape. Let us try to plot it. Average waiting time was the one which we wanted to plot. Check out that despite of the shape of this being exponential, the shape of this is almost close to a normal curve. We have taken only sample size of 30 here, so that means we are having lesser items here. The average times is only 100 cases. We want to increase the total number of cases. Let us clear the data and let us try to actually get in more samples here. Okay, so let's open the sampler again. And we are going to collect more samples this time instead of only 100. So I repeat the process from it. Let me clear the data from here. And let us now create more samples from the collector. We are going to make a sample size of 50. Right? We are going to collect 200 samples instead of the 100 that we collected last time. All right. We're going to keep the speed to fastest. Let us do some work in advance. So I'm going to add in an attribute here, average wait time, and give it a formula. It would be a mean of the waiting times. So this would populate as we collect the data automatically. So far, there is no data collected. And another thing that I am going to do is I'm going to plot this simultaneously as the data populates. So you will see that when the data is going to come on this, it would be populating the graph as well. So let us start it without much ado. Okay, I may have to reload it, or too much data again. I hope my data is safe. It's saved on the. Okay. So select a data set. We are taking 50 items in each sample and collecting 200 samples. Let us start it. So see, first sample is done, average waiting time 242 and so forth. So my samples are increasing. At the same time, my graph is being populated with what? This is the mean of the sample value. That means this is going to collect only 200 total values in all, because we are creating 200 samples. Each sample contains 50 items. For each of the 50 items, we want to have only the mean value stored and plotted. See the shape it is taking. This will be by the central limit theorem. This would always be a normal curve, irrespective of that my distribution which I had originally was extremely exponential. But despite of this fact, the CLT is always holding that whenever we are going to actually take the distribution containing average of these samples, that is going to always remain something which is of a normal curve. We want to also see what is the mean value of the waiting time. Let us check out. So the mean of my population was 246. Does it hold for the CLT? Just look how closely the mean is resembling the mean of my distribution. We have just sampled 118 cases so far. It's going to go up to 200. Look at that shape. Look at the bell curve taking shape. If I keep on increasing the number of samples, this is actually going to get closer and closer to the mean value and so forth. That is the beauty of the central limit theorem. That's the topic for today. So basically, central limit theorem is actually telling us that irrespective of whatever be the original shape of my distribution, if I sample it and I take means of those samples, that is always going to result in a inverted bell, or it is going to always be a normal curve. This has a lot of implications, the statistic going further. So most probably for the session which is going to come up next, we might actually see how central limit theorem is important to making prediction using z-scores, or how normal distributions have got certain properties which are very important to statistics. So just by having this distribution as a normal has a lot of implications, because for normal distribution, there are some properties which always hold. Okay, this is going to be an exactly great normal curve here. We are almost close to reaching a 200 samples now, and we are almost close to reaching a perfect bell shape. So can you imagine that this distribution is a result of sampling data from this entirely skewed distribution? This holds true for any kind of distribution, whatever may be the original shape of the distribution. By the central limit theorem, the means of all samples is always going to result into a beautiful normal shape distribution, which has a certain property which we can discuss in the next session, wherever we are joining next. All right. This was about the central limit theorem working into an actual demonstration that we took some real data, we created a sample of the, we created a distribution of the means of the samples to demonstrate how central limit theorem works. We also saw some data into how the law of large numbers work, where the distribution of samples is almost similar to the distribution of the original population, but the distribution of the means of the samples is always normal, irrespective of whatever shape this might have been. That is the beauty of central limit theorem. Thank you so much. If there are any questions, I am open to questions now. You can share your questions on the chat or the YouTube live. I believe there are no questions at this time. If in case there are any questions that you may have later, please feel free to send me a mail on sachin.gupta@methodai.com or at sachin.gupta@mvn.edu.in. Both of the email IDs I constantly check. If there are any questions, please feel free. If you watch this video later, if you are watching it live and have a question later, thank you so much for your time.
Thank you once again, Dr. Sachin Gupta, for this engaging and informative session. And thank you all the participants. As always, we will inform you about the next webinar well in advance and invite you to tune in. Happy Makar Sankranti to everyone. Stay safe. Thank you.